Welcome, Ben Rosso here with Solid Applications, Senior Application Engineer. Wanted to thank you for attending. That is still me, still same old smiling picture. And this is number 5 in our simulation webinar, a condensed lesson series for simulation users. So just to review where we've been up to now, we did a lesson back on May 14th on the basic simulation workflow. I would call that the world according to Ben. And I also did some details on meshing and contacts. So that's complete. And the restraints and fixtures lesson on June 2nd, that was completed. Applied forces and loads we did, that is also available to view as a webinar like all the rest of them. Working with materials and some practical, what I would call street tips, back pocket tips was last week. And now today we have understanding your results, which to me means slicing and dicing your plots and giving more meaning or a better chin scratching look at your results. So all of these webinars are available online, except for today's, which has not been recorded yet. So you'll notice that you can watch these completed webinars, and that you can go to our website, and these are, you just have to register and you click on the link and you're ready to go. I have to say that I would say that my delivery has gotten better as I go along here, not talking quite as fast as I was in lesson 1, but I think the content is fairly complete. Now remember, these are very condensed lessons. We're trying to present a bare minimum of background to get people going. If they haven't had a simulation training class, or if it's been a while since they've had it. So our regular linear static training class is 3 days, 8 hours a day with I think about 14 lessons in it. And we're condensing this into 5 45-minute to 1 hour condensed lessons. So obviously we can't cover everything, but we do have an objective. I want you today to be able to learn what tools are available to provide clarity for your results. And what I want you to walk away with is, I want you to be able to question what you're seeing and then be able to pull out more meaning for your study. That's really what my goal is, because you know, I was prepping for this lesson this morning, and I just happened to look at something I tried, a different kind of plot, and you know, I learned something I didn't know about this model, which is a model I made, which is a model I presented previously to you all in lesson 1, and I looked at it and man, I learned something new. So when you scratch your chin, excuse me, and you start asking the question why, and you push yourself a little, you're going to find out things, you're going to learn things. So by helping you guys out in help desk cases, by making mistakes, I learned things I didn't know. And I find that's one of the amazing things about the SOLIDWORKS simulation tools, and that also includes flow simulation. And I'm always learning things I didn't know about the physical world, not just about how the software works. So question what you're seeing, extract more meaning from your studies, and you'll actually be better off, not just for that study, but your general understanding of things. All right, so we're going to look at what today's topics are. This is going to be our agenda for the day. Don't let this scare you. It's pretty long. We're going to do a quick and dirty catch up there. That's very short, just to show you, for those who weren't in my previous lessons, you know, how I like to work. Doesn't mean you have to work like me, but I find it's very fast. Default plots, the basic default plots that come up are the how to edit definition. Go to our chart options and settings. Those are the things we can control in our plots. We're going to be looking at solver messages, useful stuff. You know, you always want to know after you've run your study, well, how long did it really take? How big a study was it? Now, generally creating new plots, I'm going to go over not everything. I call this more or less the greatest hits of plots. Some of these I don't use all that often. A few of these are kind of new to me, like the pin bolt check plot, because it's not the way I generally look at, you know, pins and bolts, but I'll show it to you so you know it's there. Listing stresses and displacements and strain, node by node there. Listing connector force and listing result forces. So that's another, these are 3 more things we're going to be showing here. We're going to dig deeper in here. I'm going to show you section clipping and ISO clipping. If you haven't done either of those, then these 2 might make it worth showing up on today's webinar. Also, a couple of different ways of showing the mesh, one of which is done inside of section clipping, one is done with mesh sectioning, and then adjusting the range on our plots. And that's really a chart options function. So I might actually wind up showing that in here, depending on how I'm feeling. Adjusting the range of your color chart is a big deal. So that enables you to focus your detail. It's like changing the contrast range of a black and white photograph. Creating the body from a deformed shape. That's something that people often ask me about. I'll show you how to do that. And lastly, at the very end, I'm gonna give one last little discussion about the modulus of elasticity in various materials. And I haven't really put that on the agenda, but I've added it kind of at the last minute. And it's something that you need to know about how a linear static FEA program works. So it'll enable you to have a little more confidence even when you're looking at things that are beyond yield. I want you to know what it means when something's beyond yield. So we're going to start looking at this grouping here with a review and just go over some of the default plots and solver messages. So basically, this is going to be the review catch-up slide. I like to work by right-clicking on whatever folder I'm going to be working in. So if you right-click on your results folder, you're going to have many choices that show up in the resulting right-click menu. Some of these choices we use more than others. Like, for example, a stress plot, a displacement plot, and a strain plot. To be fair, there's nothing wrong with a strain plot. It's kind of old school. I don't have a lot of need to look at the strain plot, but some of you might be more interested in that. But because everything is kind of linear, and all three of these plots are derived from each other, they're really, if you really knew about your modulus of elasticity, you could probably live with just one of those and understand what's going on. Other plots that we use a lot, the listing of displacement, strain, and stress, connector forces, list resulting force, and then comparing results. I'm not going to go into comparing results, but it's kind of self-explanatory, so I'll let you play with that one in the privacy of your own office or your own kitchen, as the case may be, during a lockdown. So regarding the default plots, you can go into your simulation menu and you can go to the options. It's down near the bottom of the simulation menu, and you can change what the default plots are. My experience is that it's not really worth changing that because there's never any exact set of default plots that I always want to see. So I pretty much live with the standard ones, which are a stress plot, a deformation plot, and a strain plot. If I need to see other plots, I'm just going to add more plots. That's all there is to it. There's no one answer that says, I need to see these, unless you're a person who says, I never need to see the strain plot. Get it out of there. Let's not bother with it. Basically, these are the three default plots that will show up at the end of your study. You can right-click any of your plots. Here you can see the plots that came out as a result of a particular study, and you can show or hide them at will. If it's shown, the option will be to show it. If it's already shown, the option will be to hide it. If it's not shown, the option will be to show it. You can also double-click on a plot, and it will show. If you right-click a plot, you can get these three things you can control: edit definition, and your chart options, and your settings. And right away, if you haven't done this before, that kind of becomes a little daunting, like, oh, where do I change, go from a discrete to a continuous plot, or where do I change the units, or which one of the, you know what, it doesn't matter. You don't have to remember this. Feel free to forget which one controls which, because it's a one-stop shop. If you click any of these three, it's going to get you into an interface where you see all three of them. So that's something that they did several years ago that really was a massive improvement. I always say it's the little things sometimes that are the biggest improvements. By giving us three tabs, when you click either one of these, you can jump from one to the other very quickly. So you don't even have to remember which set of controls which. Why they call some edit the definition, why they call some the options, why they call some the settings, I don't know. But really, once you right-click on a stress plot and you pick one of these, all three of them are available to you. That's a beautiful thing. So let's talk about defining a stress plot for starters. So when you define a stress plot, you get to choose what the type of plot is. You can see here, you got your von Mises stress, that's most common. There will be a default von Mises stress plot when you finish running the study. So most people gravitate towards von Mises. We learn in engineering school, it's the most accepted basic stress plot that there is. SX and SY and SZ, these are directional stresses. They're useful. I'm going to talk more about these later, so I'm going to move on from them now. Shear stresses, that is really more of a niche type of plot. So for those of you who have knowledge of shear, you might find that in certain cases those are really useful plots to have. But you know, this gives an idea of the depth of the functionality in SOLIDWORKS products in general, that even if they're things you don't use very often, you might find one day that you need these and you're going to live and die by this for a week. So having that depth in the functionality is great. The principal stresses, the first principal stress is often used for brittle materials as opposed to von Mises stress. The second and third principal stresses, you can read about those in any strength of materials textbook. They are commonly used. I probably should have put this one last. The energy norm error, it's a kind of obscure accuracy check that kind of checks the difference between the average of the stress in an element averaging compared to all the nodes around it. So when you have very, very high values in certain areas, that might give you an indication that you could probably put a finer mesh or a mesh control there. It's kind of an accuracy check on the local variation in energy. And then a contact pressure plot. Now, contact pressure is going to be useful when you've got a contact condition between two faces. So you can look at that. We actually show that in our simulation training class where we have a shrink fit. And a contact pressure will enable you to see what the contact pressure is between one face and another face. All right, so let's look at stress plot definition. I mentioned the SY and SX and SZ stresses. If you use the advanced options, which are down here, and you choose an axis, that's going to change the X, Y, and Z coordinates into cylindrical coordinates. Now, SX is going to be radial, SY, which I've chosen here, is going to be circumferential stress or tangent or hoop stress that we like to call it. And SZ is going to be an axial stress. So if you choose an axis that's based upon a cylinder or something like that, you're going to get cylindrical coordinates on the SX, XY, and SZ stress. So another option you could use, and I tend to use this when I'm doing circumferential stresses of various types. I'll really want to just show my stress on a certain entity. So I'll choose this option here, show the plot only on selected entities. Again, this is still part of the advanced options. And then I'll choose either a face or a body. Almost always I'll choose a body, and that's the name of the body that I chose. Then I will generally make sure I don't have average results across boundary for parts selected. Now, this is a little bit of a digression in terms of the topic of, using SY, XY, and Z stresses and using an axis as a reference. So let's table that for a moment and talk about averaging results across the boundary for parts. This has been disturbing me enough that I recently had a conversation with the simulation support people about it. So what it does is if you have two components, faces that are touching each other, it's going to average the stresses at the nodes that meet between the two faces. So you're going to have a node from one face and it talks to a node from the other face, and it's going to average the values between them. So in my opinion, this is a major gotcha. It's something I never actually need to use. And if I do use it, or if a customer is using it and they're getting erroneous stress results, I have to remember to go check to make sure that this isn't checked, because it often will give erroneous results. It's what I call a gotcha. Now, where would you conceivably use it? You would conceivably use it if you have two components, the exact same material, that are bonded together. So if they're bonded together and you don't use average results across boundary for parts, there's going to be no loss. You're still going to have very similar, if not identical, results at those two sets of nodes. So I don't have a lot of reason to ever check it. I don't gain much from checking it. And if you have different materials, let's say an aluminum touching a steel or a plastic touching a brass, you definitely don't want to average the results across the boundary for parts, because the stresses are going to be instantly different across the boundary. So by averaging the results, you are forcing an erroneous result. So my advice would be leave this unchecked, and if you never check it, it'll never hurt you. So that's kind of a gotcha street tip that I want to let you know about. And you need to know to look for it, and it's in your advanced options. So you're not going to see it unless you look at your advanced options. So make sure just to keep that unchecked in pretty much all cases. I really don't have much of a reason for ever selecting it, even if I do have identical materials that are bonded together. There's no particular advantage to me. All right, so let's take a look at one of these where I've done cylindrical coordinates. I'm getting a little further down in the weeds now. You can see there's an axis here, and I selected the axis, and I have chosen Y stress. And what that gives us is hoop stress. So an example where you might use this is if you have cylindrical pressure vessels. Everybody wants to know what the hoop stress is on a cylindrical pressure vessel, and this will give it to you. And you can see it, all the way through the thickness. And we're going to go into section clipping down the road, so you can actually look inside and see what the stresses are inside the thickness. But this is the way that you calculate a hoop stress, which is probably the most common reason why I would use an axis as a reference in my advanced options and choose SY. You also might choose SX. SX will be radial, and that will show you how far something moves away from or towards the axis. I used that in a study recently on a help desk case, and it showed me that a collar actually didn't necessarily just expand. It actually kind of moved sideways because it had a little bit of play. I learned something. All right, so we're looking at our chart options. Up to now, we were looking at the plot definition, right? The edit definition tab. So our chart options, what do we get to control in chart options? That's this tab right here. So minimum and maximum annotation flags, we call these the flags. When you're looking at stress, typically, von Mises stress, it's a scalar quantity. Here we're looking at a deformation plot, but it's resultant deformation. So that's a displacement plot, and you can see where it's bolted down. This model has basically got zero displacement, and where we're pulling on it, pulling up here, you got maximum displacement, right? Everything is a positive value. It's an absolute value. All right, it's because it's the resultant displacement. That's what this is a plot of. However, if you choose, in this case, I chose displacement in the Z direction. Now, Z direction has positive and negative values. You can see here we have a negative value, and you might notice it's a symmetrical model, and the Z direction is left and right here. We're pulling up on the model, so we're almost the same values at positive and negative, but you need to scratch your chin and look to see, positive and negative values if you're doing one of these types of plots. So SZ goes left and right. Now, I flipped the model so that the positive side is on the left because that's where our minimum and maximum flags are. So we're looking at it from this side, which is unfortunate, but that's really my positive Z direction. So you can see as we pull up on this model, the material on this side is moving inward towards the center. So it's moving in a positive Z direction, whereas the material over here is moving to the right, and that's in a negative direction. So that's our minimum value and our maximum value. We expect them to be pretty close to each other, right? So this is validating that it's a symmetrical model and everything is in order. All right, so just beware when you do these SX, SY, and SZ plots, whether it's stress or displacement, you're going to be getting positive and negative values, potentially. You may not get any negative values, but you need to know that you're expecting positive or negative values. You might get a value, if we were just pulling something off to the right, we'd only have negative values, and probably on this end, we would wind up having a big fat zero there. So be aware of your signs, all right? Another thing in your chart options you control, this is kind of changing gears here, but still talking about chart options, is what your numeric display is. So you get control over scientific notation, a floating or a general decimal. To be fair, I almost always pick floating these days. Scientific doesn't help me out. I don't need to know that something is, 10 to the 5th megapascals or something like that, or 10 to the 9th pascals, 10 to the 10th pascals. What I really want is engineering notation, and I've actually myself submitted that enhancement request 2 or 3 times. Anybody feels like being a really good, active citizen in the SOLIDWORKS simulation world, jump on your customer portal, put in an enhancement request asking for engineering notation. So with everything will be to the 3rd or the 6th and 9th power. You know, I have customers say to me all the time, I want engineering notation. We need to put in more enhancement requests asking for engineering notation in our plot output in SOLIDWORKS simulation. If you want to join the club and join that battle, I would really appreciate it. All right, chart options, some more things in chart options. This scale plot here, the legend, this is, you know, what tells you what the stresses are in the color chart. And by default, they're going to be automatic. So whatever the maximum stress in your model is going to be the top red region of your plot, and the minimum value is going to be your blue region, right? So you can also uncheck this option here. You can see here it's unchecked, and you can enter some other value. Sometimes I see people enter a higher value than the maximum. I don't see much utility in that because really it's just going to compress your color plot, and you're just not going to see any red. You know, if your maximum stress is 48 megapascals and you set this to 100, you're gonna see green and you won't see any yellow, orange, or red. It's just like you don't have as much color in there. There's not. It's kind of a backwards thing to do, but I see people do it now and again. On the other hand, if you say, look, I know I'm beyond yield, but I want everything beyond a certain value, like in this case, the yield stress is 36 megapascals. So I would set it for that, and then everything that's going to be higher will just be flat out red. So you see a larger red patch in here, right? But what this will do is between your value of 36 or 30 or whatever you have set here, between there and your lowest value, you will have the full color range, so you have a little more detail in that region. So if you're interested in some other regions below that, then this will give you more color detail there. All right, now let's look about plot settings. That's the 3rd tab there. We had the definition, chart options, and then settings. So in settings, we get to control the fringe options. So you'll see here, point, line, discrete, or continuous. Point and line, I just don't find myself using them. Point doesn't really give me anything I can make use of. Line, very little more than that. You know, the colors it's just harder to see. So really the choice is between discrete and continuous. So if you have a continuous plot, you can see it's a smooth transition of color, which has been averaged node by node. And it's a really a tour de force achievement of display that it will give you a plot like this. Or you can actually look at the old school method of discrete plots. Now, a lot of people, especially in the modern world, don't like discrete plots. But if you've got some older engineers who are going to be in your audience, who are going to be reading your reports, that you're going to be presenting to, guys who have worked in NASTRAN and PATRAN and been doing ANSYS for years, if you present your results with a discrete plot like this, where you've got stripes in a color range and your legend is going to be showing up in stripes also, you'll gain a little bit of credibility with these guys. They won't think you're some kind of, you know, young engineer who doesn't understand FEA. This, you know, it also is a way of admitting, look, FEA is an approximation, so I'm not going to claim to know exactly what the stress is in a certain area or in a certain spot. So I'm going to, you know, I'm admitting the limitations of FEA, so that it gives you a little credibility in that regard. So, you know, I myself actually prefer the modern way of seeing a continuous plot, but discrete has got a long history in the world of FEA. Plot settings. So we get to control what the boundary options are also. That's the next thing we control. So you can see 3 options there: none, and model, and mesh. So what do we get with those? Now, if you choose none, it looks like choosing shaded in SOLIDWORKS. You don't see an edge, a black edge here. You don't see a black edge here or a black edge here. If you choose model, you're going to see the black edge at the model boundaries, at the boundaries between the surfaces, okay? Unless it's a tangent edge, right? So you can see here we have little black edges and all that kind of thing. So that looks like shaded with edges in SOLIDWORKS. Then you can choose the mesh. And the mesh is going to paint the mesh boundaries on the outside of your part. And that's useful if you're getting some of that triangulation in your stress results. If we look right up here, you can see little bits of stripiness or triangular shapes. that kind of is an indication, if that were a high stress region or a rapidly changing stress region, that I might want a finer mesh there. So when you see the triangulation there, and then you put the mesh over the top of it, you can see that that's going along a mesh boundary, okay? And you know you have a node here and a node here and a high quality mesh, so you almost have, you know, a 3-node triangle here that you see with this blue region. So the mesh will give you good information. Now, one of the other things I can say about the mesh plot, putting the mesh in your plot settings, if you zoomed out, there's sometimes looks like you're looking at it through a very dark screen, and it may put you off. So it may not be appropriate to look at when you're zoomed out, but you zoom into an area and it will give you lots of guidelines of the mesh around your detail. So it's more, I tend to use it more when I'm zooming in on something. Okay, another thing you can get from your results folder is the solver messages. So you run a study completes, you get the little bing, and you right click on your results folder and you choose solver messages. It's at the top of the menu. So here what I'm looking at is a long menu, and this is right near the top of it. So sometimes it'll be near the top of your screen. Just look up near the top of the right click menu on the results folder. Solver messages gives you the gospel truth of what actually happened in your study. It will give you what your solve time was. Now, sometimes it sits around and seems to dither for a while before it tells you it's actually solving the study. It is, you know, making up the stress matrix and the deformation matrix and all that kind of stuff before it starts. But when it starts running to the solution, that's how long it took to solve it. It's 5 minutes. I'd call that a medium small study. I can also confirm that by the degrees of freedom count. The degrees of freedom means that it was solving 511,000 equations and 511,000 unknowns. So when you were in college and you solved the Cramer's rule solution on a 3x3 matrix, and you saw what a pain in the behind that was and how mistake prone it was to calculate that by hand, that's 3 equations and 3 unknowns. This tool is solving 511,000 equations and 511,000 unknowns in 5 minutes. It also will tell you the number of elements and the number of nodes. Now, the ratio between nodes and elements will change if you have a draft quality mesh. You don't have as many nodes. The number of nodes you might have on a draft quality mesh with this number of elements might be 50 or 80,000 as opposed to 170,000. The ratios change less if you have really long, skinny items. Big, chunky items, you wind up with a lot more higher node to element ratio. But it just gives you a good, quick, and dirty picture of what went on in your study. So if you're thinking of running your study again, you may as well change it. Oh, wait a minute. Was that the 1.5-hour study? Or was that the 5-minute study? Right click, solver messages, say, oh yeah, it was a 5-minute study. I'll just go run it. Okay. All right, so we'll go to the example here. And I'm going to run over to simulation. Okay, so the first thing I want to show you is just what a basic stress plot looks like. So, you know, we're going to go into this basic stress plot here. I am pulling vertically on this model. You can see if I look at it from a right side view, it looks like this. One of the things that I like to do when I'm not sure about something is I will go and animate my study off of a right click. And when I animate it, first thing I'll do every time is I'm going to stop it and I'm going to put more than the default 5 frames in there. I'll go usually between 10 and 15 frames, and I'll slow it down to something under 100. That's just a number for the speed. I've discovered somewhere around the 60 to 80 to 90 is a recent range. And what it'll do then, it'll make up a dozen frames first, and then it will start oscillating it slowly. Now, this is also really valuable when you have multi-body studies. All right, so then you'll see components that are, bonded with or have contacts with no penetration. You'll see them pulling apart from each other. You might wonder what's this little shelf going on in here. You can zoom in there. You can see how it's behaving. You can see what the stress looks like in there. And I find what this does is it gives me a qualitative picture for how the model is distorting. It's not just for the boardroom. I find often when I go to my guru in Texas and I say, Ramesh, what's going on with my study? I'm having a hard time understanding this. One of the first things he'll say is, animate the plot for me. We'll take a look at it and understand qualitatively what's going on with it. Okay, so animation is your friend, and animation is not just to make a fancy picture to impress the boss's boss in the boardroom. All right, One of the other things, let me go in here, I'm going to right click this plot and we're going to go into edit definition. And this is where you get to see it doesn't matter if I choose edit definition, chart options, or settings, I get to all of them. That's where I chose what kind of plot it was going to be, a plot of what kind of stress. This is where I choose my units. Note in the east side of the Atlantic here, megapascals as opposed to pascals. If you don't like dealing with massive numbers, use megapascals. I've got that set as my default. Under advanced options, that's where we can do things like show it as a tensor plot or change it from node values to element values. I'm going to set this one to element values and you see what that looks like. So element values, also this is something that will appeal to the old school guys. They're used to looking at plots that look like this. Let's go back to the edit definition. Go to advanced options and set this back to node values. And here you can also control the deformed shape. So if I look at a right side view here, you'll see that it has automatically placed the deformation scale of 11. You can also read that right up here. That will normally be showing at the top left. You can set this to true scale, and it's going to be true scale of a deformation plot, the same thing. So if you set the scale the same on all your plots, they're going to just look the same. No matter whether it's X deformation or Y deformation or X stress or Y, it doesn't matter. If you set them the same, if they're all automatic, they're all going to set to the same scale factor and they're all going to have the same deformation but different color charts. Or you can do a user-defined one where you say, well, you know, I really want to just set this with a deformation scale of 3, whatever. I'm going to leave this like it is. We're going to go to our chart options. Okay, so here we have our maximum annotation set. You can imagine that our minimum annotation would really just show us where the stress is least. That's not particularly interesting, so I'll turn that one off. Plot details, we'll turn off this guy. Plot legend, we'll turn off the legend. I'm going to come back to the maximum and minimum values later. Then here's where you control your type of numerical choice and your numerical precision. So you can see here I've got 1 decimal point on floating. Lastly, I think, did I set this back to, yeah, node values, okay. Lastly, on our settings is where we can change the style and change the fringes. So first let me set this back so we're seeing it with nodes. I'll get back in here. I'm going to jump straight into settings, which will put us on the 3rd tab. And I'm going to change this to a discrete plot. See what that looks like. There we go. So now you've got instant old school street credibility. And let's go back and go back to the settings. Set this back to continuous. And I'm going to show this with no boundaries. You can see what it looks like here. There's no little black lines on here. If we choose the model, we'll see the black edges like shaded with edges. And then if I choose mesh, now we'll see the detailed mesh coming in here, or mesh. There we go. So now you can see where all the detail is on this plot. All right, so when you see little bits of triangulation in here, this will help you to understand how the actual mesh is influencing the color chart. Do I need a finer mesh in here? If this was really critical and I was concerned about it, I'd say, yeah, I definitely want to put a finer mesh in there. Now let's go and look at something else here, ISO clipping. Here's a plot that's been ISO clipped. So how do we get into ISO clipping? Well, all you do is take a plain old stress plot, right click, go to ISO clipping. And that will bring in a ISO clipping manager. So let me stop a minute. This plot, if I look at the other plot here, this plot is showing that the maximum stress is about 48. This is a plastic that doesn't actually have a yield strength, but the tensile strength is about 40, and I'm guessing the yield strength is about 36. So humor me, and we'll figure that yield strength is about 36 megapascals. So on ISO clipping, if you right click and choose ISO clipping, you can set a threshold here. So I set a threshold of about 2/3 of what I figure my yield stress to be at 24. So there's a slider, you can drag it up and down and change the values. All right, and you'll show more or less. So sometimes, let's say I might set that, if I think my yield stress is 18, I set it, my yield strength is 36, I might choose half that value. So this is going to show everything with a factor of safety of less than 2, right? by making that number lower, you're actually putting a little more context into your iso-clipped plot. So let's say I'm doing this because I'm concerned about the holes. I want to look at what's going on in the mounting holes. I can go in here and I can actually see what's going on with each one of these. Okay, great. So that's our iso-clipping option. It works really well. I'm going to go back to my original plot. I'm going to show you one other thing that you might find really useful. So here's my plot. I've got my maximum stress sitting right on this region here. And I want to know, well, yeah, but what about all these other corners where it's pretty high? One of the things you can do is you right click in the background and you can choose probe. Now, if you've done a lot with your plot, while, if it's been on for a long time and you've made one or two changes to it, something, you might not have this probe option sitting here on the right click menu, and you just right click in the background. If it's not there, you can always go and just right click the plot and choose probe. So probing is one of these other things. I didn't put it on the agenda, but it's an important thing to know how to do. First of all, when you're probing, your model is going to be in an undeformed shape, because what it's doing is it's showing you the original location of the nodes. All right, so you can probe at a location. And I like to show the mesh, because then I know, especially if it's a high quality mesh, where the nodes are. So I can click on this guy. I know there's a node in there. Typically, I don't really want to see the location or the element number. I might, but a lot of times if I'm probing in a number of places, I just want to see the value. So I want to see this a little smaller. I know there's a node somewhere around here, so if I click near there, it'll put a node right on that guy. Come on now. They're a little bit jumpy sometimes. So, and I'll click over here. I'll click over here. And that will give me another node there. Come on, baby. You can. I know you can move. We'll put another node over here and a node there. So now I've got several nodes in here. I like to tend to arrange them just so I can see them. And you know what I usually do with these? I'm setting up a screenshot, right? That's typically what I'm doing. So now you can see how that stress is changing as you move away from that maximum in the middle there. So probe is a really cool thing. Now, you can do a number of really valuable things with probe. I'm going to right click in here and clear my selections. One of the things you can do is you can select an entity. So an entity can often be an edge. So if you wanted to linearize your stress through the thickness of something, if you put a split line through the thickness, you could then select that edge. So if I select an edge here, that's going to plot. It's going to give me probed values on all the nodes along that edge. So that's an edge running from here to here. And one of the interesting things you can do if you do that, now you can always do this, by the way, with manual selection, but I find it's very useful if I actually have a particular edge to pick. So in that case, what you can do is you can plot that. And this here is a plot of the stress values going from one end to the other, node by node. And if I look at that plot, you can see we're going from this edge all the way to here. And what can you do with that? Well, you can actually save that out as a CSV file and bring it in to an Excel spreadsheet. So that's a useful thing to know how to do, is probing on an entity. You can also, if you're interested in using that edge again and again, you can save that as a sensor. So you can recall that sensor over and over again. So plotting it, saving the plot, and saving it as a sensor, I think are fairly useful things to do. You can play with that in the privacy of your own office or your own kitchen. Okay. Having done that, let us look at a displacement plot. This is a basic resultant displacement plot. Can you tell from looking at it what the deformation scale is? Well, if you're not sure, look up here. The deformation scale is 1. Now, there are a couple of interesting things you can do here. This is showing you that the maximum deformation is right at this point right in here. All right, so this is a study in which we're pulling up vertically on this surface in here. And we're bolted down, and we have almost no displacement where it's attached. We have a virtual wall, so this thing cannot move downward anywhere. And if I look at this plot, its deformation scale is 1. If I want to get a little bit more exaggerated picture, you can actually get into your chart definition right by double clicking on this information thing, and it brings up the definition. It's kind of a party trick. So now I'm going to set my deformation scale to be automatic, and it will look like that. All right. Now, another thing I could do is I could do a Z displacement plot. This is what I showed you in the presentation. So my Z displacement plot looks like this. Now, if we look at our universal coordinate system, Z is left to right. So if I look at this from a right side view, we're seeing positive values here. Z is pointing to the left. So let me flip this around to a left side view. Okay. Now we see positive Z going to the right. We know that this guy's pulling to the left, that guy's pulling to the right. And you could probably confirm that by animating it. So if I tilt it up a little bit, and this is a good example of where animation will probably help you. Now I've exaggerated the deformation scale, all right, and I'm going to right click this guy. We'll animate this thing, and we'll do our 12 plots, and it'll create 12 frames. And we're going to just wait while it creates those frames, and you'll see what it does. Now, unfortunately, the animated version of the plot can't be saved in the part. You can save it out as a separate video file, as an AVI. You can see down here, there's a save AVI file. It would be nice to be able to save the animation with the plot so you could just go click on it and animate it again. But unfortunately, we're not able to do that. And this one in particular has a lot of nodes, so it's fairly slow, but we're almost there. You're going to get to see what it looks like. So what I'm particularly interested in showing you is what's happening in the Z direction. All right, so here we have 12 frames, and now we're animating it at a slightly reduced speed. So now you're going to see it actually start doing its animation back and forth. Okay, so it's moving back and forth, and I'm going to zoom in here. If you look at this region right here, you can see where the maximum is. That you can see this wall is moving to the right. Well, that's what you get when you exaggerate your deformation scale and you animate your plot. You can really see how things are moving. And the same thing on this side, it's moving to the left. So you might have wondered exactly, well, how much does it move? How much, how extreme is it? Are my holes moving very much? Well, my holes aren't moving much at all, but these regions right here are moving a fair amount left and right. So if that's what interests you, you can find it out in a plot like this. Is that worth the wait? Say yes. Okay, great. Strain plots. Strain plots kind of get short shrift in SOLIDWORKS simulation. I'll just show the default strain plot. Element values is really how they're calculated. I don't find myself looking at strain a whole lot unless I've got a model like a long coil spring where I have large deformations. The stress is very low. I might want to look at some of the individual strains. Generally, there's nothing wrong with strain. It's more of an old school way of thinking, so I don't find myself looking at strain all that often. Now, I want you to know something about what SOLIDWORKS simulation actually does when it calculates. First, it makes the mesh. You tell it, mesh my model. Then what it does, it looks at the boundaries of your model. It looks at all the restraints and the contact conditions if you have multiple bodies. And then it applies all the loads. And if you apply any displacements, it will apply those. And then it will then try to come to an equilibrium. And what it's really calculating is the displacement of each node. So when it's done, what it's got is what's called the stress matrix and the displacement matrix. Really the deformation matrix, I should say. Now, from the deformation, what it's looking at is the deformation from one node to its neighbor, and it's backing out of the deformation what the strain is. So those two nodes had a start distance, and then they got a finish distance, and it calculates the strain from that. It's all based upon the deformed model. So strain is backed out from the deformed model. Then it applies the linear stress strain curve, which is a sloped line, the Young's modulus, and based upon the stress plot, it calculates the strain. Excuse me, based upon the strain plot, it will calculate the stress. So stress is backed out from strain, which is backed out from deformation. So really what this tool is doing is calculating the deformation. or the displacements. And then the other results, because we have a linear assumption of stress versus strain, it comes up with what the stress is, which is why you can have a stress that is 5 times yield, and all it's doing is saying, look, it's a linear static study. I've got a linear stress strain curve. I'm just telling you what the stress is based upon the strains I've got, which are based upon the deformations. Your material may or may not support it. More on that topic later when we close out this presentation. Okay. So let's come back to our PowerPoint, and we're going to talk about what we've gone through so far. We've done our edit definition, our chart options, and our settings, and we've looked at the solver messages. So creating plots is our next topic, and let's talk about that. So if you're going to create any other plots, you're going to right-click the results folder, and some basic types of plots we create all the time: displacement plots, strain plots, fatigue check plots. Not a big fan of that unless I'm using SolidWorks Simulation Professional and actually doing a fatigue study with the actual SN curve. I'm going to kind of warn people off of this. It's kind of you don't really have the information to really get accurate fatigue out of plain old linear static SolidWorks simulation. Not a big fan. I'm not going to tell you don't do it, but it's not the same as running a fatigue study. Pin bolt check plot. It's a plot that's kind of interesting, but I usually will actually get something else from my results folder to see my pin and bolt checks. And then the result equation plot. Now that's a very interesting kind of plot. I really kind of never played with it until a few days ago, actually. And tell you what, I learned something new. It's a great little plot. So let's go to the example and take a look here. You've seen basically, that we can right click, we create a stress plot, create a displacement plot. I'm going to create a Y displacement plot here. So I go to displacement. The Y direction is straight up and down. Let me collapse my feature tree so it's not in the way. Y is straight up and down. I'm going to choose UY. We're not going to do anything fancy. I will leave it on the same displacement scale. I'm going to, under advanced options, I'm going to make sure that we're showing, we're not doing anything specific there. Now, because we have potentially positive and negative values, I'm going to show a minimum annotation. Because I have a virtual wall in the bottom, I'm not expecting anything is going to move downwards, so I'm thinking I'm going to have a 0 minimum flag, okay? We'll leave the numerical settings the same, and then we will do a continuous plot with model fringes. So let's take a look at that plot. Okay, so we're actually getting a slight downward motion at the edge of the hole. So it's not near upward in the bottom of the part where the virtual wall is, but as this thing bends upward, it's actually bending the inside of that hole down. Well, you know what? I didn't expect that. I learned something new. It makes sense that that's happening. Now, if I'm interested in what's happening around here, we know that our displacement is almost a millimeter up here, where this thing is flexing a fair amount. We're pulling up on it after all with 200 pounds, that's about 800 newtons, right? So we're pulling up on it quite a bit of force. And we expect the center of it to move, but if we're curious about this, what could I do? What if I just said, look, I really want more detail in the low region. So I'm gonna set my chart options to cut my maximum value way down from here. Something like, I don't know, a millimeter, millimeter and a half. And then everything above that will be red. Now, chart options, we know we can go right here and pick chart options, but you can also double click on your legend. If you just double click on the legend, it brings up chart options. Again, no big deal. You can always choose anything else. For me, I just go wherever my cursor is. If I'm over here, I click on that, go into edit definition or settings, whatever I need. So I'm going to manually define my maximum value of displacement, and I'm going to set it to like 0.1 millimeters. And let's see what we get here. So now you can see everything here in red, that's the uninteresting area. And now I get a lot more detail here showing exactly what the behavior is. I get the full color range from this region all the way to here. So that gives you an idea of how you can slice and dice simply by changing the range of your chart options, and you can actually get a lot more detail where you want to see it. Okay, now let's look at something else. I'm going to hide this plot. By the way, if you haven't done too much with your plot, you can probably right-click in the background and hide it. Again, if this menu is not there, you'll just right-click on the plot itself and hide it. Okay, let's do a pin bolt check plot. I actually have one here. You right-click, you do define pin bolt check plot. So let's look at the one I've got already, and I'm going to edit its definition, and we are simply going to show it. So this is listing any bolts that have exceeded the strength value for the bolt, have exceeded the factor of safety, and those that haven't. So this is the listing of the ones that are okay. I've got 4 bolts. I click on each one. It shows me the bolt on screen, and it gives me the value for the factor of safety. So these should be pretty similar to each other, right? It's all factor of safety is a little over 8 because this is a symmetrical model. We're just pulling straight up on it. You can look at the details and select all bolts, for example, and you get the full listing of all the bolts. And you'll notice that when you click on each one, here's foundation bolt 1, shear, axial, and bending moment. Click on each one, it lights up in the graphics window. There's bolt 2, there's bolt 3, and bolt 4. Now this interface here is very similar, and this is a little bit kind of wonky here because it doesn't act like it shows. So I have to show it and then hide it again, or show something else to get rid of it. I'm going to try to jump ahead to the next section momentarily. And if you really want just bolt information, you can right-click on your results folder and choose list connector force. And any connectors you've got, you can, again, segregate them. You can pick on an individual one. You can pick on bolts, pins, springs, whatever you want to choose. So I'll choose all the bolts. You can run down here. You still get the same interactivity where I click on the bolt and it gives me the values for it and it lights it up on screen so I know which bolt is which is again typical of SOLIDWORKS, a really nice kind of two-way street. So it'll give me all the information about a particular bolt and it will light it up in the graphics window. So this is my way of looking at results force on any bolt connectors that I put in there. One thing to know is that you need to have defined on those bolts the strength data when you create them. The strength data isn't used in the study, it's used in the post-processing. Okay, right click. I'm going to show you another kind of plot, and I want to talk for a moment about the material in this plot. So I'm going to right click on this body here, and I'm going to edit the material. And when we look at this custom material, we'll notice that the elastic modulus in megapascals is about 2,400. And so throw that in your back pocket. So I'm going to do what's called a result equation. I've got this plot already, but I'm going to make a new one for you. And it takes a moment to calculate. It brings up a dialog, and it chooses a stress out of the blue as a default, but you can change that. So I'm going to divide this, and I'm going to start a parentheses, and I'm going to choose from amongst the strains that are available to me, just the regular equivalent strain, and I'm going to multiply it by 1,000,000 because I want my results in megapascals, because the von Mises stress is just going to be in pascals. So I'm dividing it by 1,000,000 times the strain. So we'll use node values, and I'm going to do this, and we're going to say, okay, chart options, we're going to use the same type of values that I've had before. And we're going to let this gin up for a moment and take a look at what it gives us. Again, this is something I discovered not too long ago. Now, the plot in itself, it almost looks like something you'd see at you'd buy for a kid's birthday party. Here's my maximum value. If I look at my minimum value, it's almost the same. These are very, very small differences. Now, what am I showing here? 2,601. This is a kind of reality check on our Young's Young's modulus, the elastic modulus, which was 2,410. So we're using von Mises stress, which is again kind of an approximation. We could try the same thing with the first principle stress. This is a kind of a reality check that I discovered not too long ago that says, hey, you know, this is showing me something very, very close to my modulus of elasticity. Stress divided by strain. That's what the modulus of elasticity is, isn't it? Huh. Interesting thought. That's one of those that I'm presenting this almost like it's a party trick, but it's an interesting thing to think about. So if you're ever concerned, where could that be really cool would be if you have an assembly with different materials and you do the same plot. Then you'll see different, pretty constant colors for different components. I like that notion. All right. So basically, I kind of covered creating the various types of plots, including the results equation plot and the pin bolt plot. I also took care of listing connector forces and result forces now, and listing displacement and strain. Let's jump on that. All right. So if you're going to list something here, your choice, if you right-click the results folder, is list stress displacement plane or connector force and result forces. This is going to give you basically a table with top 5 or 10 or 20, whatever you tell it, nodes, where the top 5 values for either stress, displacement, or strain. It's interesting. I'm probably not going to demo this for you, but basically when you choose this, you're going to choose stress, displacement, or strain, and how many percentage points of the top percent do you want to show. So this can be a fairly long list if you want it to be. List connector forces. This is what I showed you before, and you get, if you have pins and bolts and spring connectors, whatever, you can segregate it to show only some of these, or show all the specific connectors or any of the specific connectors that you want. Connector forces, again, they're going to show with the values you have, and if you have strength data put into your bolt connectors, what you'll see is they're either going to show up green or red. If they're green, they're good. If they're red, they've exceeded the factor of safety. So if you built in a factor of safety of 3 and they exceed that factor of safety of 3, they're going to show up red. That is nice to know. And then result forces. Now this is one that I am going to show you: a free body force, reaction force, a contact or friction force, or connectors forces. It's the same result force dialogue, but I'm going to jump into the example here and show you that. So let me jump into this model here. Okay, so this actually is a pretty good one for connector forces. So I'm going to right click on the results and I'm going to say list my connector forces. And I can choose all connectors. I guess I'll do that. And you'll see here that I've got 4 bolts here and 4 bolts there. Now these bolts are put into sheet metal, so their results may not be accurate. So I'm going to just go past these bottom 4 and start looking at these next ones here. It shows the shear force, axial force, bending moment, and torque moment. You'll notice that they're all colored green based upon the strength data and the factor of safety I put in there. So this is a useful thing to know. Now let's do something else here. Let's look at reaction forces. I'm going to, resulting forces. I'm going to right click and say list resultant force. Now here you have your choices of what you're going to do. I'm going to choose a free body force, and I'm going to choose a face. Now the only faces you can choose are where you've got a restraint or a load applied or a contact condition. So I'm just going to pick a face like this, for example, and you can see here that we're getting X, Y, and Z values and a resultant on a given face. So you can sum them up. Sometimes if you can sum up all the forces you've applied and choose the same faces you applied them to and do a reality check. Or you can look at your restraints. You know, this model, what are my restraints on the model here? I fixed the outer boundaries here. You see that? So I could do a right click, list result force, free body force, and I'm going to choose these faces here, and that should do a reality check on the force versus the forces that were applied. Okay, so that'll tell me the resultant is 1960 newtons, and it'll give me the values in the direction that they were applied in. So everything was applied in one direction here. Great. So that kind of will enable you to do a little reality check for the entire model on your resultant forces. That's, again, one of those chin scratching things. Well, you know what? You might have applied a force in this direction and a force in that direction, and you don't know what the resultant force is. Just pick your restraints, get a resultant force for the whole thing. Okay, so we've kind of covered the listing of forces, listing connector forces, listing resultant forces. Now let's dig deeper and look at some of our plots. So we're going to talk about section clipping, iso clipping, showing the mesh, adjusting the range. We've already talked about that, so I'm going to kind of jump past that and creating a body from the deformed shape. So when you section clip the model, what you're doing is you're basically slicing right through the model, and you want to show all the stresses inside the model on a face. You can do that by picking one of the default planes, front, top, or right, any other plane you've added to the model, or a flat face, and you can drag through the model to get an offset distance, or you can manually enter an offset distance. So if you plot on the section only, that's this option right here, what that's going to do is just show the plot on the section. All right, now in my settings, what do I have set for my model boundaries? Mesh, right? There we go. Okay, another option, you can show the mesh on the section plane. Now I'm not plotting on section only, I'm just going to plot the whole thing, but I'm showing the mesh just on the section plane. So that puts the mesh on the section plane here, and you can really get a good detailed look at it. Can you probe that? Yeah, you can. Valuable. All right, I've shown you iso clipping. I've shown you the value of iso clipping, that it will actually display values above and below a chosen threshold. So we like that. It's really a useful tool. Mesh sectioning. This is fairly recent. I believe this was brought about in 2015. So what this will do is cut along element contours, and it will pick the elements closest to one side or the other side of a face, maybe with an offset to that face. And lastly, there's creating a body from a deformed shape. So you simply right-click the results folder and create a body from a deformed shape. Your choice will be saving to a new configuration in the same model or a new part file. This does not save the stress matrix or the deformation matrix, merely a deformed body. I can see somebody getting ready to raise their hand with this question. This is not going to give you the ability to say, well, I'll do a study where I apply some of the loads, and then I'm going to save it as a deformed body, and I'm going to apply the rest of the study with those loads and that stress on it, but remove a restraint and change a load. This won't enable you to do that. It's simply going to give you a deformed body, and it might do something like that if your deformed body is something that crushes, let's say, and you want to use that crushed body in your model down the road. But this isn't going to give you a partially deformed body and bring over all the stresses with it. You need SOLIDWORKS Simulation Premium to do that, where you've got time-based loading and time-based restraints. And you can do that in Simulation Premium, but that's not what this does. This basically would just save out a deformed body. So in the example here, we're going to jump back to my initial guy. So here, we're going to show one of my stress plots. Let's go to, I like this study. Let's see, no, this study is actually a more, I think, a more interesting study. And we will simply show a simple stress plot. And this is a sideways load and a longitudinal load. So we're getting a lot of force in two directions. And I'm going to right-click the plot and choose Mesh Sectioning. So my maximum stress, by the way, is right here. Okay, so that's a pretty interesting thing, right? To see this maximum stress there. I'm going to right-click and do Mesh Sectioning. And I'm going to choose the front plane by default. And I'm going to start dragging that front plane backward until I get to the region right where that mesh is, that stress is maximum. Maybe I'll even choose a different plane. If you want to see it from the other side, you can choose the right plane. All right, so now I'll drag it back again, and I want to get right down in on where right where the elements are showing that really high stress. And you'll see that I've gone to a negative value here. So I can, I can set this to, well, maybe, negative like 13.0. It'll pull it back just a little bit. All right. Or make, you can dial this in very closely and see a really close-in picture of what the mesh is doing as you look at a region of interest. Okay. So mesh sectioning, if you look at it and you look at what's happening all around the model, this gives you a really good picture of what the program thinks is happening inside the model. Wow, I like that one. Okay, and hide that plot. Now, what about saving the model out to a deformed shape? Well, just right-click the results folder and create a body from a deformed shape. So what you can do is choose it to make a new configuration or make a new part file. I'll choose a configuration and I'll just do that. And it will export that. Well, actually, it won't export it. Will create that configuration, which you don't have to keep if you don't want to. And when we're done with this, it will create a deformed body. We'll come back to that in a moment. All right. Come back to the slideshow, and oh, it was having a difficult time doing that one. So I covered section clipping and ISO clipping, showing the mesh in a couple of different ways. Remember, when you do a section clipping, we can also show the mesh in the section clipping as a flat face. I talked about adjusting the range when we were in chart options and creating the body from deformed shape. We're going to come back to that in a minute and see if we got a decent result. One last thing I want to talk about, and this is kind of a big deal. Now, I mentioned this before, that what SOLIDWORKS simulation does is it uses your linear modulus of elasticity, your Young's modulus, and it calculates a strain, and from that it backs out a stress. Now, it will do that based upon a modulus of elasticity that may go beyond yield. So when your modulus of elasticity is, or excuse me, when your yield stress is 50 megapascals and you're showing 150 megapascals for a given material, what the real world material stress strain curve looks like is something like this, right? So when you get results up here, you're nowhere near accurate. You could say, well, my results are just beyond yield, I'm not far off, but you might have another material that has the same modulus of elasticity and the same Poisson's ratio, and it has a different yield strength. So let me give you an example. A high strength alloy steel and plain carbon steel. They have about the same modulus of elasticity, very, very close to each other, and the same Poisson's ratio. They're both about 0.29 for Poisson's ratio. So if you swap out the material from one to the other, you're going to get almost identical stress and strain and deflection results. The difference is going to be that if your stress value falls in this range between the carbon steel and the high strength steel, that it's accurate for the high strength steel, and you're beyond the point where this linear modulus stress strain curve applies. So for your carbon steel, when you're way beyond yield here, all you know is you've exceeded yield. Plastic deformation, you don't know if it breaks or it bends or what. All you know is that you're beyond it. You don't know how accurate it is. Yet, if you're under the yield strength for a higher strength material in this range, you can consider your result very accurate. So it's calculating based upon a linear stress strain value or a particular slope. That's what linear FEA is. Okay, so I want you to know that you can change material to something 3 times as strong with the same stiffness, basically, the same modulus, and you're going to get the exact same plot, except you'll know that your results are under yield, and therefore they're extremely accurate there. Okay, so that's a kind of a caveat about what a FEA linear static analysis does. If you want to see behavior in this portion of the curve, then you need to actually have a nonlinear study with a nonlinear material curve, which is not what this series of lectures is about. All right. All right. Really quickly, I'm going to just try and run back and see if I actually got that model and did we get that, did it create that plot? No, it did not. So we failed. I've never done it with this model before. Oh yeah, and that's the deformed body. Do we have it? No, it wasn't happy. No bodies. So we're going to just go back and punt on that one. Not sure why it was having difficulty with it, probably because of the details in my mesh. So let me come back here. I'm about done for what I'm going to show you in this study. We've actually exceeded the 1 hour, and we've gone through 4 lessons, and now today we've gone through the 5th lesson, understanding your results. Really appreciate you coming by for this webinar. You'll be able to shortly, probably later today, catch this 5th lesson on a video if you want to see it again. And I want to thank you for attending. And we're going to put our heads together and come up with some more presentations for you all for topics that we think are going to be useful for the majority of you. It might be simulation, it might be SOLIDWORKS functionality, but we're really liking this. We're getting good feedback from our customers, from the people who attend these, and we really appreciate you taking the time to come here and spend some time with us. If you have any questions, give me a shout. You all know where you can find me, and my word of wisdom today is don't lose the plot. Thank you all for attending.